Okay, as announced, this talk is going to be about how we tried to hack the Switch. The story behind this talk is that earlier this year, multiple parties announced publicly on Twitter and similar channels that they seemingly have found a bug in the Nintendo Switch, or at least in the chip that is being used by Nintendo in that gaming console. Although nothing was publicly released. So I met with a friend earlier this year. We were hacking on another project, and we thought to ourselves that, well, maybe we could try as well to just hack the Switch. If other people were capable of doing this, we should be able as well. And we kind of succeeded. We got almost there. We were a bit late to the party, and almost 30 minutes before the first before a description of the bug was released, we actually found the bug, which was a bit unfortunate, but well, it was a nice journey and we learned a lot, and I thought this would be a great talk to give. So a few words what this talk is going to be about. This talk is not going to be about the stuff that Nintendo did with the operating system or stuff like that. It's not about how browser exploits work on this platform, how you can start, I don't know, pirated games or homebrew or whatever you might want to do on a hacked console afterwards, but more on how a fundamental flaw in the chip itself and the boot ROM of that chip that is being used can be abused to execute, to circumvent all the security features on that platform, and how to execute your own code. I'm always talking about we, and now I can advance the slides for whatever reason. There we go. I'm always talking about we. I did this, as I said, with a friend together on the right side. I'm on the left. I'm a security researcher at Rapid7 right now, doing completely unrelated stuff at work. I'm doing internet scanning and building honeypots there. If you want to reach me, you can reach me via Twitter or old school on IRC. On the right side, this is Serge. He's currently living in Dublin. Originally, he's from Poland, and he's right now a freelancer in DevOps and hardware, and also doing security-related stuff there. You can reach him as well, and we know each other because we play CTF in 2 different teams, but over the time, we got very close friends, like the 2 teams of us, and we have the same interests, that is hardware hacking and well, all kinds of low-level firmware stuff. So yeah, we just teamed up, and here we are. A bit about the hardware that's being used by Nintendo. If you've never seen a Switch, I'm sure you have, but this is one. It looks like a tablet, and the nice thing about this is that you can detach the controllers here. And I mean, it's a portable console. It has a battery and everything, but you can also just take like a dock that's supplied with this thing, and you can attach this via HDMI to your TV and just put it in there, and then you have a stationary console like this, and you can take the controllers off and put them like in a holder that you can see there, and then you have a stationary console. Yeah, the hardware that's being used, this thing is based on an NVIDIA Tegra X1. This is an embedded chip from NVIDIA. It has multiple CPU cores, Cortex A57 and a Cortex of quad-core A57, a quad-core A53, together with an NVIDIA Maxwell GPU, which is, for the power consumption and the size of this thing, quite impressive. It also has 4 GB of RAM, but yeah, every phone has 4 GB of RAM nowadays. This bit about the software. The software is completely custom. Nintendo did not use any kind of off-the-shelf operating system for this. The operating system is called Horizon, and it's actually quite modern. It has all the fancy security features that you can imagine. It has a user and kernel mode split, and an X bit so that you can execute stuff on the stack, for example, if a stack buffer overflow. It now has ASLR. With the newest version, it even has ASLR in the kernel. So it has actually quite a lot of security features. The boot flow is customized by NVIDIA. NVIDIA supplies closed source bootloaders. If you're big enough, somebody like Nintendo is, you can also get the source code, but usually they don't give this out. And Nintendo, of course, customized the bootloaders for this. because yeah, they need security for their consoles. The Tegra X1 that is being used in the console, that's the SoC, the main chip which contains all the GPU and everything, is internally called the T210. That's their Nintendo, their NVIDIA code name for this thing. I think it's the successor of the Tegra K1 that's being used in a bunch of tablets. For example, the X1 has also been used in the Google Pixel C. And there is also already a successor. Even when Nintendo announced that they're going to release the Switch, the successor was already out. But yeah, it takes time to design such a thing and write the software and everything. So yeah, it might have been too close of a call to just use the X2. What's interesting is that the X2 looks like a complete redesign. If you compare the data sheets, this thing is completely different. It uses different CPU cores. The architecture inside looks different. Yeah. For the X1, the nice thing is it's an off-the-shelf chip, so you can actually get documentation. It's a 3,000-page datasheet, or rather technical reference manual, that you can just download after you create an account with NVIDIA. They don't ask you for an NDA or something like that. It's incomplete, even though it has 3,000 pages. All the security stuff is mostly undocumented, but it's still very extensive. So you can still gather quite a lot of knowledge about what's going on in the system. As I said, there are a bunch of proprietary NVIDIA bootloaders. There is a boot ROM that loads code from a mass storage device like an eMMC. And the boot flow on the development board, we will see this later, consists of, I don't know, 4 bootloaders, I think. Most of them are closed source, but I mean, you can reverse engineer them, but they are undocumented. But it's actually not very hard to find out what they do. Yeah, the Switch has custom bootloaders, and they have the security features of that chip enabled. That means that you cannot just load your own code on that platform and just execute your own operating system like Linux or whatever. Because first of all, I think the hardware is subsidized, so they want to try to sell games and make money by selling the games. And of course, they want to prevent piracy. So you can't just copy games, or also they have certain quality standards. They don't want everybody to write games that might be, well, not good enough for them to have them on their platform. So they're keeping a close eye on what people can actually run on that platform and whatnot. And this is what we're going to hack. You don't have to be able to read this, but this is a block diagram of that SoC that I copied out of the reference manual. You can see that this thing is a beast. It's essentially a complete, well, let me say computer, whatever a computer is nowadays, and one single chip. On the top here, you can see, on the top left, you can see the main CPUs. On the bottom here is a memory controller, and there are a bunch of bus systems between this, so that the CPUs can access the DDR4 memory. There is a GPU here, a bunch of peripherals here, like a UART, a serial console, or a serial port. Whatever you do with it, doesn't have to be a console. I2C, SPI, all kinds of stuff. And everything is connected using these crossbar switches, which are bus systems. Think of it like if you have a main board and you plug in a PCI Express device, something like that. This is essentially a bus system. Not exactly like that, but the concept is the same. Yeah, so what's interesting is that here is another CPU. Down here is another one. This is a full-fledged Cortex A9, which they can use for audio. I don't know if Nintendo does use this, but this core is actually has enough features to boot Linux. I don't know if anybody tried this before, but it should be possible. Here's another small core. That's what we are going to look at mostly, because this is the so-called BPMP. BPMP stands for Boot and Power Management Processor, or Bootstrap and Power Management Processor, I don't remember. And this thing is the first CPU that runs code when the system is turned on. The CPU, the GPU, and so on don't even have power when you turn on the CPU. Also, when this chip, or when this core executes code, the DRAM is not configured yet, so you don't have memory. This is the reason why on the top here you have 4 small SRAMs. It's 256 kilobytes in total, because if that CPU needs to run code, it has to have some kind of memory where it can put its variables, its state, whatever. And also here is a block that's called IROM, and IROM is the boot ROM. This is the first code that this BPMP processor executes when the system turns on. And this code in the ROM is responsible for checking a lot of stuff that is security related. And this is the code that enforces that you can't just run whatever you want on this platform. The nice thing about this chip is you can buy this chip. This has not been the case on other gaming consoles before. You always had to buy a gaming console, hack it first, get code execution there to get an idea what this thing looks like on the inside. Now we have documentation and we have something that we can break. Because we can just buy, we can also break a switch, but this is way easier to work with if you want to exploit something. I also brought my board with me here. This is the thing. There's just some small UART adapter still on there. The cool thing is the security is disabled. We can just load code and just execute it and just play around with the platform without having to break any kind of crypto or, I don't know, exploit the web browser on the console first to get userland execution, then have a kernel exploit to get more privileges and so on, to figure out, to run our own code to break even more of the security. So we can just load code on there and play around with it. And I got a student discount. These things, if somebody's interested, is around 250 euros with the discount. This is what, the board, as you can see, is a main carrier board. Is a main carrier board. And there's a main carrier board, and on top there is a module which contains all the important components. This thing here, and it contains the main SoC. That's the chip that you saw the block diagram of earlier. Some RAM. The eMMC, which is a fancy SD card, essentially on a chip, which is way faster than a normal SD card because it just has more pins, so a bigger bus, and some power supply stuff, and a Bluetooth and Wi-Fi chip. This is the switch mainboard. It's all a lot smaller. I stole this picture from iFixit, by the way. They do nice teardowns, and again, this is the SoC. It doesn't say Tegra X1 in there, but it is one. That was found out pretty early because somebody just looked on this chip under a microscope and it looked exactly like an off-the-shelf chip. Some DDR4 memory. This is the Wi-Fi chip. I think it's a different Wi-Fi chip. It doesn't matter for this talk. And I don't even know what these chips are. I think this is some USB controller thing. Here's the USB port. Here's a power port. Here, somewhere here is a cartridge port because you can put game cartridges in the console. So you can talk to these and so on. This port here, I think, is for the eMMC. It's conveniently placed on a nice add-on board. So you can rip this off, read it out, make backups, whatever. Very nice of Nintendo to socket these. Okay, now that we know how the system looks like, how do we own it? This is the boot flow of the system. We can see I colored these boxes differently depending on what CPU the code is running on. The red ones is the BPMP. This is what we are going to care about. And the blue ones are the CC plex, which stand for CPU complex. These are the big ARM cores that are started later by one of the bootloaders, and then code is executed there. This is usually where your Linux runs and so on. So this is the boot flow of the development board. This is not the boot flow of the switch. The switch has way less of these bootloaders here. I don't think it even has any of these, but I did not look at the switch bootloaders, so I don't really know. So what happens is when the system turns on, the first thing, as I said, that's executed is the boot ROM. The boot ROM has multiple paths. I even left out one here because I, again, did not look at this. It's the warm boot path. If you put your device into suspend, it goes into this warm boot path, but no idea how it works, to be honest. And the first path here is the normal boot path. It tries to load something that NVIDIA calls NVT boot from mass storage, which runs on the BPMP. This is the first bootloader. That bootloader, again, loads NVT boot CPU, because that's a bootloader that then runs on the CC Plex. Here, after loading NVT boot, power management firmware is loaded into that core so that you can do all kinds of power management, like put the device into suspend and so on. This is handled then on the BPMP CPU. And then that NVT boot CPU loads a bootloader called cboot. Never heard about it. It's able to load Linux and does some fast boot stuff for Android tablets and so on. Then this usually loads either directly Linux or normally it loads U-boot. And this is actually the first component that you can get source code of. And then it jumps into Linux and it does its thing. The other path is interesting. It's called RCM. It stands for recovery mode. If the boot ROM fails to load NVT boot, for example, from the eMMC because the eMMC isn't there or it's corrupted or whatever, then it goes into this RCM path. You can also force this by pressing some buttons, and then you have an USB device that you can use to load code into the chip, and then you usually load something that's called NVT boot recovery, which then runs from RAM, and then you can talk to this thing, and you can reflash the eMMC or whatever mass storage device you have on your board or on your device where the operating system lives. Of course, we can't just use this because RCM as well enforces security. So everything that you load has to be signed with a certain private key from Nintendo. Otherwise, and a signature is checked, if the signature is wrong, the thing will not execute this code. Yeah, this is true for this path and this path. And also, after NVT boot is loaded, NVT boot, of course, checks signatures of the next stage and of the next stage and of the next stage should security be enabled. Yeah. The boot ROM itself, what it does is does a bunch of things. First is basic hardware bootstrapping. It has to configure some PLLs, so everything on the chip has clocks to work with. Then it determines what to do, either boot into RCM or do a warm boot or where to load the bootloader from. It does this by looking at so-called fuse bits, configuration bits that you can only write once and then afterwards read. After that, it tries to find on the mass storage device the thing that's called BCT, the boot configuration table. This contains mainly parameters for the memory controller, so that you have DDR4 memory or DDR3 or whatever else the memory controller can talk to. You need to do link trainings and all that fancy stuff, so you need to configure this memory controller with the right values. And everything is specified in the BCT. Also, the BCT tells the boot ROM where to find the bootloader, what bootloader to load, and the hash of the bootloader. And the BCT is signed, so we can change that. If you change the bootloader, the hash does not match anymore. You can't change the hash in the BCT after you change the bootloader because that would break the signature. So everything is in order and you can't just load code without having the private key. The ROM is interesting because the ROM is the root of trust. If you defeat any kind of security in that ROM, you can load whatever code you want. This, as I said, is the root of trust, so you have to trust that boot ROM. If you can't trust that boot ROM anymore, you can do whatever you want on that platform. The ROM, although, is secret. You can't just read it out, even though we can execute code, because we all know if something is secret, it's way more secure. And but what we can do is we can try to torture the dev board and to try to extract that ROM somehow. We will see later how we did this. So the boot ROM lock, how does it work? Well, yeah, let's look at the technical reference manual. I just searched for secure boot and you don't find that much, but you find this table. This table describes two important registers. The first one is called SBCSR0 and the second one is called SBPIROM start 0. And if we look at that, the first one, the SBCSR0, we can see that its reset value is 01. These are bits. The X means don't care, not implemented. The other ones are either 0 or the last one is 1. If we look at what this means is the first bit says secure boot flag. If that's 1, we are booted into secure mode. So obviously on reset, that's the case. And then another interesting thing is this PIROM disable. The documentation doesn't really tell us what this means, but this text already tells us a lot. It means protected IROM disable. We know that the IROM is the ROM itself where the BPMP executes the code from. And if it's set to 1, it means that this seems to be disabled. And on boot, it's 0. The other register, and to be honest, I have no idea why they implemented this, as BPIROM start. And it says this specifies the offset from the start of the boot ROM to the protected region. This register is only programmable while in secure mode, which means secure boot flag in the register above needs to equal 1. This is on reset set to OX1000. And what this register does is even if the boot ROM is locked, you can configure how much can be read of the boot ROM. Like the offset from the start to whatever is specified in this register is readable even though it's locked. And this is only writable if we are in secure boot mode. Like if this last bit here in the SBCSR0 register is set to 1. And it's not only that only this register is writable if that flag is set to 1, but also the other one, this SBCSR0. So the idea is that you can lock the boot ROM and write protected register so that you can't unlock this afterwards. That's the theory. That's what we guessed. So I wrote some code that just tries to read the boot ROM to see what's going to happen. So these defines here, these are the addresses of these two registers, SBCSR0 and SBPIROM start, because I wanted to know what the values of these registers are after the boot ROM ran and loaded our code, because we assume that the boot ROM is going to be locked there. This is the address of the IROM, and we're just going to dump it. So what it does is it initializes the UART. That's why that UART thing was still dangling on that board. And we're dumping the two registers just using some printf, and then try with the hex dump function that I wrote to dump the 96 kilobytes of code where the IROM is. So let's see what it does. This is the output that you get. I shorted this a bit. We can see that SBCSR0 is set to OX10. The reset value was OX1. So something wrote to that register. SBPIROM start 0 wasn't touched apparently because it's still OX1000. So we should be able to read out the first 4 kilobytes of the ROM. And that's what we can see here. It starts at this address, it dumps some stuff. I shortened this here, and here's address OX1000. And at address OX, so this looks like code. This actually looks like ARM code. I can tell not because I'm a disassembler on Lex, but because there is a trick to ARM code. If you see a lot of E's here in this byte, and this byte, and this byte, this has something to do with how instructions are encoded on ARM. This is a good pointer that this might be ARM code. Also, if you disassemble this, you can see that this code actually makes sense. But here at OX1000, we just get some weird stuff back. Not, well, seemingly randomly looking stuff, but always the same pattern. And if you disassemble this, it's the opcode for jump to address 0. Why? No idea. I never tried to jump to address 0. Maybe this chip resets or whatever. So if you try to execute this code here after the boot ROM is locked, it does whatever, but not going to execute the ROM again. And also, we can't read it. Okay, so we confirm that our assumption most likely was right, how this ROM locking works. So what it seems to do is that this SBCSR0 really controls the ROM visibility, because we can tell that the dump showed that the value of this register was 0x10, but the reset value is 0x1. So something, and 0x10 means secure boot flag is disabled, so we can't write this register anymore. And PIROM disable is set to disable. So we can conclude that something in the boot ROM, just before jumping to our code, writes into this register and disables the read access to the boot ROM. Because initially the boot ROM has to be unlocked because the code needs to be executed and data needs to be loaded from that ROM and so on. Okay, we somehow need to skip this instruction. And the idea was we apply something that we call voltage glitching. We can't debug the boot ROM using JTAG and just tell it to skip that instruction or whatever. So we somehow need to convince the chip to not write into this register. So we apply voltage glitching to do this. So to find out how this voltage glitching works, I'm going to explain to you very briefly. You can have multiple semesters of lectures about this, how microchips work. But very brief, I'm going to explain how usually a chip works. It's not always the case, but most of the time that's correct. So one of the building blocks of modern chips is a D flip-flop. That D flip-flop is used to save data on every rising edge on this clock pin. So the pins that you can see here, the D pin is a data pin, and the clock pin here is a clock pin. On the left side you have inputs, on the right side you have outputs. The Q is an output, and the Q bar is the inverted output. The reason why you have this inverted Q there is because you can get it for free when you build a flip-flop, basically. So it's nice to have. You can, if you need the inverted output signal, you can just spare an inverter after that. So what happens is you apply a clock here that goes from low to high, stays a while high, goes from high to low, and after a while it repeats this cycle. So you have, well, yeah, a clock that's ticking all the time with a certain frequency. And every time there is a rising edge on that clock pin, the data is moved, whatever the bit is, 0 or 1, is moved to the Q output and the Q bar output. This thing is also available in level-triggered variants, so every time this pin is high, this data movement happens, but normally you use edge-triggered flip-flops. So D flip-flops are used to save values. You somehow in a chip have to store things, like CPU registers, for example, the simplest example. You have to have some kind of storage on a microchip. And this, because physics, if you have a real flip-flop, there are certain performance characteristics that are important to how this thing works. The three that are important to us is the setup time, the hold time, and the propagation delay. What exactly this means is on another slide. Then we have also combinatorial logic. This is what you know as digital circuits. This is the stuff that you might have seen in school with a bunch of gates that are just connected to each other that do some kind of logical function. Yeah, and the typical example that you hopefully all know is a half adder, which just adds two 1-bit numbers, which is displayed here on the right. You have two inputs, A and B, and you have a sum output and a carry output. Because if you add two 1-bit numbers, you get a 2-bit number out because it might overflow into the next bit. It's basically the next decimal, no, not decimal, binary point, binary place rather. And also here we need to be careful because that signal that travels from the inputs to the outputs takes time, because all these gates need time to switch and settle. So it takes some time for the input values to travel through all these things to the output value until the signal is stable on the output. That's called the propagation delay. Now, if we combine these two things, it looks something like this. And a modern CPU, for example, why does it run at 4 gigahertz and not 40 gigahertz? I mean, we can create clocks that are, I don't know, 40 gigahertz. I mean, apart from the electrical problems that you're going to get because this is a very high frequency. The reason for that is that a chip usually works like this. You have this D flip-flop, which saves some value. You have some combinatorial logic, and then you have an output flip-flop that, again, saves the value. So what happens is you have an input. The clock goes to the rising edge. For sake of simplicity, let's assume that this clock here and this clock here, that there is no delay between these two. In reality, of course, there is a delay usually because the signal takes time to travel through this line to this flip-flop. But let's assume we have some data here, a new clock edge comes, then it switched to the output. At the same time, the value that has been calculated by the combinatorial logic in between is already here at the output flip-flop. So when the clock edge rises, both of these flip-flops will hand the value at D over to the Q output. And so we get basically the result of the combinatorial logic calculation on the output, and at the same time, the combinatorial logic circuit is being fed with a new value to calculate through this flip-flop. And the reason why we can't just raise the clock frequency however we want is that all these delays with the flip-flops and the combinatorial logic and the setup and hold times that are needed need to be taken into account. So if the clock switches faster than the signal takes from to go from here through this logic to here, we're going to get garbage out. The setup and hold times, I copied this thing out of a data sheet from a flip-flop. You can buy these things as dip chips or whatever, still available if you want to put these on a breadboard and play around with them. And we can see here the CP pin. This is the clock again. We can see the data pin, and we can see the two outputs. And as I said, this flip-flop is edge triggered, which means every time we have a rising edge here in the clock, something will happen down here. So this happens 2 times here and here. And if we look at the D pin, these shaded areas here mean that it doesn't matter what this D pin is, because the chip, the flip-flop will only act on the rising edge of the clock. So we can see here on the at the time of the rising edge, D is on a high level. And so it takes some time to propagate through this chip, and the Q output at some point in time goes high. Same deal here, just the inverse. We have a rising edge again, the D pin is low, and after a while, the signal again propagates through the flip-flop, and the level here goes low. Now, what about the setup and hold times? The setup time describes the duration, how long before a rising clock edge occurs that a stable signal needs to be present at the input. This is what you can see here. You can see here that the clock goes high, but at the time here, the signal on D already needs to be high even before the clock occurs, the clock edge occurs. Then we have the hold time. This is similar, but after the rising clock edge. So we can see here that we have the clock edge, and here again is a duration specified TPLH, which says, no, TH here. So for this amount of time, the D input needs to be stable, either 0 or 1, otherwise bad things will happen. And then again, we have the propagation delay, and the propagation delay is just the time, how long it takes from here when the rising edge occurs until the D value is actually forwarded to Q. This is this TPLH, for example, here, that it takes the signal to travel from here to here. The setup and hold times, why are they even there, or how can we find out why how high they are? The logic gates are nowadays built most of the time, again, in so-called CMOS technology. So you have MOSFETs, N-channel and P-channel MOSFETs. This is just an N-channel MOSFET to see what these things actually do. this thing is a switch. If the signal is pulled to low, this will stop conducting and the LED turns off. So power will flow from here through the LED. It can't pass this MOSFET, so the LED will be off. If we pull the so-called gate, this is this pin here, high or up a certain threshold, then this thing will start to conduct, and the current can flow from here through this resistor, through the LED, back to ground, back into the battery, so the LED lights up. This is what you do with that switch here. You connect this gate basically to the supply voltage, and then this thing starts to conduct. If you leave the switch, then this resistor will discharge, like pull all the charges away from here, and this will be pulled to low, so it turns off again. So every time you press the switch, the LED turns on. If you release it, it turns off. The gate here needs to be charged. It behaves like a capacitor, and a capacitor, if you put a voltage on the capacitor, it takes some time for it to ramp up and actually pull the charges into the capacitor to fill it up. Then there is a certain threshold in this MOSFET where it starts to open up and starts to conduct. It starts to conduct current to turn on the LED. And a logic gate or a flip-flop consists of multiple of these things. So again, every time you chain these things, it again takes more and more time to charge up these gates to make them do, or discharge them to make them do stuff. So this adds up, and this is how the propagation delays also affect the setup and hold time. So the setup time, for example, is you need some time to charge up all the gates of the MOSFET in such a D flip-flop or wherever else, and the hold time is that all this stuff needs to propagate through this logic gate or the flip-flop until the signal really is stable on the output again. Oh yeah, and if we of course violate these periods, then this thing might not turn full on or not at all, and the LED might only be half on or something like this. So the MOSFET doesn't really do what we expect anymore. Yeah. What's interesting is that if we increase the voltage that we put on the gate, we can make them switch faster. So because if we apply a voltage, some current will flow into the gate, and if we have a higher voltage according to Ohm's law, we will get a higher current, and a higher current means that we can current is charges per second, that we can put more charges into the gate capacitance and thereby turn the MOSFET on faster, or discharge it faster and turn it off faster. When we can charge the gate faster, we can switch faster, because charging the gate is essentially a switching operation. And that's the reason why overclockers increase the core voltage of their CPUs when they raise the clock. Of course, you can't do this. You can only do this up to a certain point, because there are more effects to this. The chip gets warmer because it dissipates more power. It switches faster. It dissipates even more power. And at some point in time, the chips just break. But what would happen if we, on purpose, decrease the voltage instead of increasing it, like overclockers do, to violate these setup and hold times? Things will break. So we get a so-called glitch. So the logic circuit will not do anymore what it's expected to do. We just need to do it right to get the effect that we want. So what should we glitch? We saw earlier that most likely that SBCSR0 thing controls the ROM logout. And initially the ROM is not locked, so that's the state that we want to keep. So SBCSR0 has to be written by the ROM somewhere right before leaving the ROM code and jumping into our code. And And the write to that register travels over multiple buses. I don't know if that register is exactly in this block here. I just assume it because it says system configuration system register, so it would make sense for it to be there. So if that boot ROM code tries to write to that register, it has to issue a write on this bus. This bus decides, oh yeah, that is this in this memory region. I need to forward it over this path to this bus. And then this bus decides, oh yeah, it's that system configuration register. I need to forward it to this block. And then inside that block, there is some logic that changes the register value and so on. So these are kind of like, imagine that earlier with the slide with the flip-flop, some logic, another flip-flop, some logic, another flip-flop. And there's multiple stages of these like in this path. And we only need to disturb one single part of this bus transaction to cause problems. And we don't even care how we are going to disturb it. It just needs to break somehow. It can write a wrong value to that register. It can write to the wrong address. The write could be too late for the clock cycle to happen, and it is happening, but it's happening too late. All this kind of stuff. The problem with that is we can also hit the wrong spot. So either we are too violent and take away too much power, then the CPU just crashes or stops, locks up, or we do it at the right spot. Then we glitch not the right instruction that we want to glitch, but another one before or after, so we don't get the desired result that we actually want. Also, we still need to run code. It's not enough to just glitch away that register write. Our code that runs after the ROM still needs to be able to read out that ROM and dump this to the serial port so that we can get a dump of the ROM. So how are we going to find the sweet spot? The idea is that we look at the eMMC traffic, the traffic between the SoC, like the main chip, and the eMMC, because we know that the boot ROM has to load code from there, because it loads our code from there. We wrote that in there, and the SoC is configured to look at the eMMC for loading the code. So we can sniff that and just try to find out what the last transaction is that happens there. So we have a stable timing anchor from where we can try different things. So we hooked up an FPGA to do that and wrote some code to analyze the eMMC traffic. And we used the last transaction as a trigger. So we wait for that trigger, and then we wait a random, not random, but we wait an amount of time. After that, we glitch. So we take away the power to the chip. We wait for our code to execute or not. Depending on what happens, we see if we can actually dump the code. If not, we adjust that time and we repeat the whole thing. And we just write a script and just leave the thing running. And every time we increase $time a bit to sweep over the whole region and see if we can hit the sweet spot at some place. This is an image that I did while doing all of this. We needed to find the right voltage rail to glitch, and these modern SoCs have a lot of voltage rails. So on the other side here is the chip, and all these capacitors here are hooked into the different voltage rails. And I took my multimeter and just beeped everything out and tried to find out what is connected to where. Green, for example, here is the ground plane, I think. And then I just soldered wires to the different colored points and measured what voltage is there. We ran an endless loop on the CPU, which just prints numbers. And when I soldered the wire, this is not something to try at home, but we didn't care if we break the thing. We just shorted the thing to ground. Usually it doesn't break. Because the voltage regulators can detect this and they turn off. They then turn on again. They see, oh, it's still a short. I turn off again after a while. and then it tries again. But at some point in time, and then we looked for crashes. So yeah, the one funny story is you can't read this because it's in pink. Also, graph coloring is hard because I ran out of colors at some point. Here is something that says 3.3 volt smoke. I hooked up this point here. I hooked it up to ground, and something on this board started smoking. I have no idea what it was because the board still works. I unhooked it, and it still. I reflashed Linux, and it booted, and everything works. Wi-Fi works, Bluetooth works, the GPU still works. I have no idea what went up into smoke. Yeah, and we looked for crashes, and we because the assumption is when we take away the power supply for the CPU, it has to stop. And we found this slightly green color here in this area to be the right voltage rail. And down here, you can see that we soldered wires to some test points, and this is the eMMC port. Kind of. There are some test points where the eMMC traffic is. So we just solder wires to there and just move them out for easier access to hook them up to the FPGA so that we can sniff the traffic.
So is the assumption that the CPU is only running on one voltage and all the other components running on the other ones, or why are you trying to? So
the question was, I'm just going to repeat for the recording into stream. The question was, is the assumption that the CPU only runs on this one voltage? No, it's not. We just tried. And this was the only voltage rail that did something. Some of the voltage rates were just turned off. We didn't know, for example, for the main CPU or the GPU at this point in the boot process, we weren't even sure that this is the right voltage rail. Because, for example, if you imagine if you have such a amount of voltage rails that you have on this chip, they are used for all kinds of stuff in the chip. Maybe for the clock generation circuit. Maybe this gets its own voltage. If we knock out the clock generation, we of course knock out the CPU as well. But this is not what we want. We just assumed that one rail that we found was the right one, and it turned out to be the right one. Pure luck. Usually you would just look that up in the datasheet, but we didn't have a datasheet with a pinout for that chip. So we had to guess. We also didn't have schematics for this module, only for the carrier board. And this module generates all the important voltages by itself. So yeah, pure guessing. This is the setup that Serge came up with. You can see the main board with all kinds of wires attached and oscilloscope probes. And this is just a UART adapter. And this is the FPGA board with a logic analyzer attached so we can see what's doing. And this board ran the FPGA bit stream, which sniffed the eMMC traffic, generated the trigger for the MOSFET that we hooked up to the voltage rail to pull it to ground, to short it to ground and take away the power for the chip. Yeah. So we wrote a script that did this loop where we glitched it, we looked at the output, we reset the board and adjust the time, reset the board and repeat, and left this thing running overnight. And when reviewing, and we just recorded everything our code spit out on the serial console. At the next morning, we looked at the dumps and we saw that at one place, it actually started dumping. It said, well, that register is still the reset value and here's the ROM. But it wasn't the ROM. It was still that EF, whatever, jump to zero thing. So we didn't think much of this. We thought that it might not have glitched correctly. We hit the wrong spot. Maybe we glitched our code. The CPU was maybe in a weird state where it was drunk because it didn't get enough power at some time, was stuck in some weird thing. So we, well, didn't care at that time. Later, it turns out I read from the wrong address. The ROM dumping worked, I just dumped the wrong address because I forgot a 0 in the address of the ROM. Yeah. And then Serge left for a business trip for a week, directly after the next day. And I was sitting at home, not having that. So this was all in Dublin. I was in Aachen. So I didn't have this stuff. And I didn't have that FPGA board. I had the code and everything. I would have been able to set this up by myself, but I didn't have this FPGA board, and I was just too lazy to port the code to an FPGA board that I had at hand. Yeah. So I tried my own setup. Because I didn't want to port the code, I needed another trigger, and this was the dumbest idea ever. I just used the reset release as a trigger. So remember when we do this loop, where we reset the board, try to glitch, adjust the time, see if we glitched, adjust the time, reset the board again. I just used this reset as my timing anchor. I then wrote my code so that I turn on a GPIO directly after. The first thing that my code did was turn on the GPIO, just a pin that you can turn on and off like on an Arduino. And I hooked up my scope, and I measured the time between how long it takes between reset release and my GPIO going high. So I essentially measured how long it takes for the boot ROM to do its thing. The idea was that I just need to move that glitching pulse then while looking at my oscilloscope shortly before my GPIO goes high, because turning the GPIO on was the first action of my code. So right before, the boot ROM must disable the boot ROM. And then I just move it around a bit until I hit the spot. That was the theory. This is what this looked like. This is a MOSFET that I bought. I just soldered it here onto this small capacitor that I ripped off the board. Yeah, it's rather small. So these things here are 0201, something like that. I even resoldered all of them that I took off.
For scale.
Yeah. So yeah, this is just ground. This is where I hooked up my oscilloscope probe, the blue wire, and the white wire is the signal line that my chip whisperer, something that you can use to glitch chips, just put the signal on to turn on this MOSFET and pull this voltage line to ground to this pad. This was my setup, a bit messier, but also a lot simpler. This is the board again, a bunch of oscilloscope probes to look at stuff. Serial port adapter, some voltage level shifting, just because everything here runs on 1.8 volts that I cared about. So and this chip whisperer here, which does the glitching. This basically does the reset, glitch, adjust timing, reset, glitch, adjust timing loop over and over again, controlled by some Python software. This wire is the GPIO that I measured, and then I measured how long it takes for the boot ROM to do stuff. This is a screenshot of my oscilloscope, and the blue one is the reset line, the green one is the GPIO, then we have the glitch pulse. Every time we glitch, this goes high, and here we have the VCC line that we are going to glitch. So right now this is at 1.05 volts, something like that. The glitch pulse is low, means we're not glitching. And this reset is low active. That means if it's put low, reset the chip. If it's put high, let the chip run. So I release the reset here, and here my GPIO goes high, so I can measure the time between here and here, and that's around 60 milliseconds, very roughly. This setup was not very good, because I said, dumbest idea ever. The timing between all the runs is different every time. These 60 milliseconds here, this time, is not true. It's not always 60 milliseconds. It jitters around by, 40, 50 microseconds all the time, so the timing is different on every single run. Also, so the ROM seems to take a different amount of time. I suspect it's this because it initializes PLLs, and these PLLs need some time to lock every time you reset, and this seems to take different amount of time every time it does that. That's just a theory. I have no idea why else that could be. As I said, the setup is very bad. That's not how you usually do it, but I just thought I'd wing it. There is no clock synchronization. I added this picture again here because I just send out glitch pulses. And if you glitch here in the shaded areas, nobody's going to care because that flip-flop is not doing anything. So we can't possibly violate the setup and hold times or any kind of propagation delay because nothing is happening on the chip right now. So if we happen to glitch here, nothing will happen. If we synchronize the glitching code, although to the clock that we supply to the chip, then we have a better chance of hitting like right in here when it actually matters. But yeah, I didn't care. Also, I don't know why overly the glitch pulse was so massive. I had to go up to several microseconds. So multiple hundreds of instructions must have been glitched there. Yeah, and we don't have a stable timing anchor because I didn't sniff the eMMC traffic, and just use the reset line as a timing anchor, and the timing differed all the time. So this is what it looks like. I zoomed in on the other side. So reset is already high. The boot drum did its thing. Here the GPIO was high, and here I injected the glitch way too late. So I glitched my code. So we see the voltage rail going low and then slowly recovering here when the voltage regulator switched on again. And this went on and on. Like I tried multiple times. Like you can see, it jitters around all the time. This, for example, is too late. This might be a bit too early. This as well. Yeah, and I just left the thing running. I just had the glitch here, and this wobbled around all the time. So the idea was, maybe if I just leave it running long enough, because I knew that the glitches would do something sometimes, maybe I'm lucky, and because of the jitter all the time, I might hit the right spot. I didn't really think that would happen. And then on another screen, I suddenly saw this. And this was my facial expression. This is the code that was running there. It said all the time, boot drum locked, boot drum locked, boot drum locked, boot drum locked. And I always checked, is the boot drum locked? Yeah, okay, then don't do anything, wait for the reset. Be glitched again, and suddenly it said boot drum unlocked, and it started dumping stuff at me. And we're like, what? And again, we can see this actually worked. Because we can see this is again the hex dump, this is what we saw earlier, same stuff. And then here at OX1000, earlier we saw this jump 0, and suddenly we get stuff back. And it looks like the other code. So we got the boot drum. This was running in a screen. I just dumped everything into a file, wrote a script which parses my hex dump code, wrote this into binary, and opened up a beer. Okay, that's how you get a boot drum. I never expected this to work, but sometimes you just need to get lucky. Yeah. So last thing of the presentation is the bug. Story about this is after you get the boot drum, you of course try to analyze this and find the bug. The way you do this is you throw this into this assembler and you look at this for a very long time. Because you need to find out what the thing does. And there are basically no strings in that boot drum. So you don't have anything, no debug output, nothing. You have to go through every single function and look at the assembler code, or using hex rays, you get some C pseudocode back when you have a decompiler license, which I gladly had because I have a license at work. So both Serge and I spent countless hours looking at this because you also couldn't Google for stuff because it was all undocumented. Nobody knew how this thing works, and nobody else published anything about this. So we reverse engineered the main boot path, nothing to be found there. We started looking at the RCM code. And it turns out the bug is actually in the RCM code. RCM, as stated earlier, this is the other path that you saw earlier when you press a magic button combination or the thing cannot boot. It stands for recovery mode. This mode can be entered on reset using some GPIOs if you press a magic button combination, or if you set a magic bit somewhere. You can trigger this by software by setting a bit in some register and then resetting the board. Then the boot ROM on the next boot sees that this bit is set and it directly goes into the boot RCM path. Or if you have a primary boot failure and also the recovery boot it attempted that you can configure didn't work. So for example, on a switch, if you rip off the eMMC of the board, it can't load stuff, so it goes into RCM. RCM itself is a relatively simple USB protocol using so-called bulk transfers. You can just throw stuff at it and read stuff from it in a certain format. And these blobs, it's complete binary format, so no ASCII or something like that. They are written to that bulk endpoint, and there are essentially two possible opcodes. There are more, but the others don't do it. It's like a NOP or something like that. It's like query some versions. You can query 3 different versions. They are all the same all the time. Or you can download code. You use this download code function, for example, if you bricked your device and you need to recover from that somehow, or during manufacturing. If these things are manufactured, most likely they will run through an automated process where they go into this RCM mode and flash the first version of the operating system there and write all the crypto keys and so on. And this will most likely be done by code that's being downloaded by RCM. So quick USB crash course, how this works, because that's important for the exploit. USB devices have so-called endpoints. You can think of an endpoint like a pipe between the host controller, that is your notebook or your PC, and the device. There is a control endpoint. That control endpoint is used for basic device management. Every time you plug in a USB device, the USB host stack is going to read some so-called descriptors, which tell the operating system what kind of device is that. Is that a mass storage device? Is that a USB serial adapter? Is that a switch? Whatever. This thing is always there. It has to be there per spec. So you always have a control endpoint. Then there are bulk endpoints. These are used for raw data transfers. You can, for example, this is being used on USB mass storage devices. If you plug in a USB mass storage device, it's going to have multiple bulk endpoints where you speak some SCSI protocol over it, and you just send these commands using a bulk endpoint to write a block, to read a block, and so on. These bulk endpoints have no guaranteed latency, so it can take a while until the bus is free, until they are actually transmitted to the device or read from the device, and you don't have a guaranteed bandwidth. So if every device on the bus is just right now talking, it might get slower and slower and slower. And there are interrupt endpoints, not important for us. These are used by stuff that have small bursty packets that need to be read or written on a regular time basis, like mice and keyboards. And there are asynchronous endpoints. That's a continuous stream of data that needs a certain amount of bandwidth without the guarantee of it actually arriving on the other side. So that could be lossy. That's used for audio sound cards and stuff like that. Because if you don't have the guaranteed bandwidth, then audio might get choppy and so on. And all these endpoints, you can have multiple of these. You can have multiple bulk endpoints, but you always have only one control endpoint. But you can have multiple bulk endpoints, interrupt endpoints, asynchronous endpoints, and so on. And all of these endpoints, in theory, can be used independently of each other. So while I'm handling a bulk transfer, I can also have a control transfer pending that needs to be answered in between or after handling the current bulk packet. RCM uses the control endpoint, of course, because it has to be there. And actually, that's not true. 2 bulk endpoints, one for reading, one for writing. And the bulk endpoint is used to move the RCM messages that are used to download code or query the version and so on to the device, and you can read back if that some error code if that worked or not. The control endpoint, of course, supports all the standard USB control transfers that need to be supported. And typical control transfers are stuff like set address. If you plug in a USB device It doesn't have an address assigned yet, so the host controller over the host USB stack tells the device over the control endpoint, your address is now 20. And then that device reacts every time it's talked to on that address 20. Then there's a get status request. We will see this later. That just returns status bits of the device or an endpoint or an interface. Get descriptor is also being used. That's for the identification of the device. What kind of device is that? Is that a mass storage device? Is it a mouse? Is it a keyboard? And so on. There are a lot more, but these are not important. Actually, for our purpose, only the get status request is important. A control transfer has a standard layout. Let's call it packet that is being sent over USB, looks like this. You have some kind of a request type that says, is this a read or a write? Who do you want to talk to, the device or an endpoint? Stuff like that. Then there is, what do you actually want to do? This tells the device stack, for example, if this is a set address or get status or get descriptor request. And then there is some W value, it's a 16-bit value. That's just some payload that depends on what the request in B request is. Then there is some W index, that's kind of the same, just with a different name. And then there is optional, then there is a length that describes the length of optional data that might be written or read from the device, depending on if this is a read request or a write request to the device. And then either there is some data here or there is no data here. So this is optional. This is what one of these RCM messages looks like. It's basically just a C struct, a binary blob that is being thrown over a bulk endpoint to the device, and the bulk endpoint, the host stack then does stuff. So here are some CMDs. Download code, for example, is command number 4, and all these version requests are 5, 6, and 7, for example. And this struct contains all the important things that the RCM code needs to know to verify that message, the signature of that message, and what it's supposed to do. It has a length, how long is that complete packet, or that complete command. Some crypto stuff. Here, we don't care, because we don't care about the crypto. And we can't break it anyway. It's RSA 2048, so no chance. Some device ID that needs to match. It's a unique device ID per chip that needs to match. Then there is the opcode. That's one of these here. Then there's the length again. But this time this is signed. So everything up to here is not signed, because you, of course, cannot sign the signature because not possible. Because you would have to modify the signature after signing it. So that doesn't make sense. So here again is the length, this time signed. The length here is just convenience for the code, so that the code just needs to read the first 4 bytes, and then it can expect that this packet has a certain length. And then when it read past here, it compares that this length is equal to this length, so that it is sure that nobody has tampered with it, because you can't change this one because it's signed. Then there's a payload length. You can attach a payload down here. That is, for example, if you want to download code, that's the code that you want to download. And this is the length here. Then there is a version that needs to match one of these here. Some arguments that you can supply. For example, for download code, it's the address in the payload to jump to. If you have an entry point that's maybe not in the beginning of the code, but farther out, you can specify that here in the arguments, and it jumps there. And yeah, something, I don't know, it's most likely never used, some key index crypto stuff, didn't look at it, didn't reverse it, some padding, and then follows the payload. Then the payload follows. That has a length described, as I said, by this field. The boot flow, that's some code, just to give you a high-level idea. Just quickly going to describe. You don't have to really be able to read this. I'm going to highlight what the blocks do. The first thing it does is it checks if you already read like the hardware ID. It tries to send you a hardware ID, and you have to read this as a first thing if you want to talk over RCM to the device. If it doesn't succeed, it just tries again and again and again and again until it succeeds, and then it sets this flag to break out of this loop. In between, because it tries to send stuff all the time, it also has to handle control requests, because as I said earlier, the bulk endpoint transmissions and the control endpoint requests can be independent of each other. They don't really have that much to do with each other. So both of these things have to be handled after another, but they have to be handled. After that, we call a function that's called RCM receive message. So we are essentially waiting for a message. After this has been sent to the host, the host can prepare a message and send it over with a code you want to download, for example. So we receive that message. After that, we check if that message is properly signed. If it's signed, we validate a bunch of fields in there. For example, that these two length fields are equal. If the code is not too much for us to actually jump to. And then we jump to a function that's called RCM prot handle message, where it's jumping to the code, or it's responding with the version information that you requested, and so on. And if that message actually tells you to jump to some code, you break out of this outer while loop, and then you return, and then the following code that called try to load from RCM is just going to jump into the code that you just downloaded, because this function checked everything for validity. How do we receive messages? This is a very convoluted function in the ROM itself, because it does complicated stuff. It's receiving receiving these RCM messages, and what it does is it always does this using two DMA buffers. So it always has one buffer where it receives the message into, and that's somewhere in memory. And it does this asynchronously. So what it does is it queues a read request from this endpoint with a length of 0x4000 bytes, because that's how big the DMA buffer in memory is. So it kind of instructs the hardware, everything that comes in from that bulk endpoint, put this somewhere in memory up to a length of 0x4000 bytes. And then it goes on. In the first loop, this again is a while loop. In the first loop, it's going to determine that it needs to read more stuff because it hasn't received anything yet. So it's going to skip this part. Then it's also going to skip this part, more on that later. And then it has to wait for the read request to finish, because as I said, it's asynchronous. It tries to process data at the same time while receiving the next chunk of data at the same time. So here, if we set this read more flag, which is here as well, if we queued a transfer of these RCM messages, it's going to wait here until that finished. When that finishes, it tells you how much it actually received, because the host can send less than 0x4000 bytes in a single packet. And when it finishes, it returns here and goes back to this loop. So now it knows I have X amounts of bytes read. So it sees if it has received enough, it says, okay, I don't need any more. So then it goes into this if, where it checks if it received less than 680 bytes yet in total. The 680 bytes is important because this struct here is exactly 680 bytes. So what it tries to do is it first reads this header of the message without the payload. If it got more than 4 bytes, then it already has this length here. So it knows most likely how much data in total it needs to receive for the message to be complete, including the payload. So then it checks some fields in there if the total amount of data it needs to receive is not too long. And if that's not the case, it knows how much does it in total need to receive. And then it goes into this if it received more than 680 bytes at this point, we received the header already, that big struct, and parts of the payload already. So then it copies the payload also into memory, into a different place than this RCM message buffer. So this RCM message buffer is the header, where it checks some these lengths, for example. And this is at one place in the memory, and the payload is in another place. We will see this later on another slide. And if it received more than 680 bytes, so it has the header put into this one place, it can start to receive the payload, that is the code that we want to jump into that other place. And it goes on and on and on until it determined, okay, I received enough enough bytes as determined by this len insecure. I don't need to receive anything anymore. I'm done here, and it returns. And then in the underlying function, this one here, the one before, it can check the signatures because it completely received the code. Okay. So to recap, this just receives the message. It does some all kinds of sanity checks already so that we don't overflow anything, and puts the header into one place and the payload into another place. This function does this asynchronously. So while waiting for this to finish, oh yeah, here for example, this is the memory layout I talked about. This is the this SRAM that the ROM has as part of its memory. Here is some handoff data in the BCT. The next bootloader needs this stuff, so the bootloader just puts it there and tells the bootloader, yeah, I loaded you from this device and so on. Then there are global variables. Then here is the first DMA buffer. As I said, it uses two buffers. It always uses the first one, then the second one, then the first one again. Here is the stack. And then here's the RCM payload buffer. This is the code that we would jump into. So what the boot ROM does is the RCM message, these 680 bytes here, will be put here into the global variables. And the RCM payload following that message will be put here into unused memory that's never touched by the boot ROM except for this RCM payload download. As I said earlier, you have to handle these control requests all the time. When this function before kicks off this asynchronous read and it waits for it to finish and actually deliver data, it does this here in this function. So USB device read endpoint 1 out complete. So it just waits for this transfer to complete. It does this in this while loop. It checks some status of the USB endpoint. And if that status says, okay, I'm good, then it breaks out of this loop here. If the buffer is ready or the endpoint is stalled at some USB thing to signal errors, then you can break out of this loop. Otherwise, it just keeps looping and polling the status. And while doing this, it needs to handle a pending control transfer. And because that also does DMA, because it's also USB, it's going to use the other DMA buffer. So we have these two DMA buffers. For example, this one here is right now used for the bulk transfer to receive the RCM message. And while it's filling that and waiting for it to be full, it's using this buffer to potentially receive and answer to control requests at the same time while waiting for the hardware to fill up the buffer. And then when it's done, it's going to switch roles and they're used vice versa. Yeah, so this is important. This does this all the time. Now let's look what that function does. That's a bit easier. It just handles the control transfer. It receives stuff from the DMA buffer. It copies that over into some other buffer, and it looked like this is this is what it receives. The request type, the request, so it needs to determine what the host wants from me. And then prepare a response and send that over in that function. So it just looks into all these fields. It looks at, oh, is this a device to host transfer? So Does the host want to read something? If so, what kind of request is this? Is this a status request? If we want to get the status of the device, we just call this get device status function, put this into this variable here. Per USB spec, this descriptor is 2 bytes long. And then it sets this descriptor variable, which is a pointer to the location of the status. And what then happens is that down below here, a memcopy happens where that response, this is the response that the host waits for on that control request because it wants to get the status. So we now have to copy that response we want to send to the host into a DMA buffer and tell the USB stack, this DMA buffer needs to be sent out to the host now. So we do that here. We memcopy that descriptor with that length that we set to 2 here and this descriptor into that DMA buffer, and then we kick off the transfer with that length. Easy. If we look at another case here, we want to get the status of an endpoint. So they again fill the status variable with some return value of the function that gets the endpoint status, and it sets the descriptor length to something. Why is this here 2 and this not? This here, this GUSBD request is the same that it uses here to find out what the host wants. So this W length thing is controlled by the host. So usually this is always 2 because the host just knows the status request is 2 bytes long. So I just supply 2 here. But this descriptor length here is used down below in that memcopy, and we control that length. That means we can copy more than 2 bytes using this memcopy function. So we are not only copying this variable that is on the stack here into that buffer, but also everything that's behind it when we set this length to more than 2. If we supply 2, we just copy that variable, that status variable. If we supply 4, we copy that status variable plus 2 bytes that are behind the status variable on the stack. And we can play around with this. So this is what that looks like. Again, here we have the message that is completely uninteresting now. Here we have the payload that we downloaded. And here we have the USB endpoint status variable. That's 2 bytes long. Scale is not correct, but. So what does the copy operation look like? If we do the memcopy, it looks like this. We copy these 2 bytes, the beginning of that DMA buffer, and that buffer then is passed to the hardware. The hardware is told, send this out to the host, and magic happens. But what if we copy 8 kilobytes? If we set that W length to 8 kilobytes, then the memcopy operation is going to copy that variable plus 8,190 bytes into that DMA buffer from the stack. So we can leak stack and a bit of stuff that we send over, but we still don't have code execution. We can only read the stack, but the stack is directly behind the DMA buffer. So we always copy stuff from here to here. What would happen if we copy 16 kilobytes plus 12 kilobytes from here to here? Like this. We overwrite the stack. And the interesting thing is on the stack in the C language is used if you do a function call to the memcopy, for example. In a function, then the CPU needs to save where it needs to go on after that function is done. And this is saved on the stack. This is called the return pointer. And when we can overwrite the stack, we can overwrite the return pointer and just change this return pointer. We don't have it to jump back into the code that called the memcopy, but we can put some pointer there and just jump into the code we downloaded here. And this happens before the signature can be checked, because what we do is, this is the main function, then we jump into this RCM thing. These are all the function names that are called in sequence. So we have this try load from RCM call. Then we have this RCM receive message where it puts the header in one place and the payload in the other place. We then wait for a transfer to complete. And the transfer never completes because we just tell the boot ROM with that length field that we want to send, I don't know, 20 kilobytes of data, but we only send 19 kilobytes. Or 20 kilobytes minus 1 byte. And then we just stop sending stuff. So it's going to wait in this function for the last transfer to complete. And in the meantime, it also has to handle these control transfers. At that point, we send this get status control request with that overly long W length value that we can control. So we take a bunch of our payload, copy it over the stack, and then the memcopy is done. The memcopy would return to this function because of the saved return pointer on the stack, which we overrode, but it never does this because we overrode that return pointer and we can jump to our payload and we can just put our code in there. And all this happens before any kind of signatures are checked because this code still receives the message. When we overwrite that pointer, it still thinks it doesn't have the complete message. So it never returns from this RCM receive message function. And that RCM receive message function comes before RCM message validate signatures. So we don't even need a signature because it's never checked. And yeah, we just put our code here into that RCM payload, and yeah, we can use this RCM to execute our own code without any kind of signature checks. This is the bug that has been found by all of these parties that were on Twitter and talking about this. Yeah, we found this as well 30 minutes before it was published. I already had the text editor open and trying to write an exploit, but yeah, then I saw the message. So what do we need to do to exploit the thing? We connect to USB. We have to read that ECE ID because that's the protocol. We then download code with that invalid signature into the memory with the right header and then the payload. We never finish the download. That means we actually set the length to a higher value than what we actually sent. And then when we are done sending our payload, we just issue that get status control transfer with an overly large W length. The memcopy happens. It gets copied over the stack. We control memcopy's return pointer, and we capture the flow of control profit. One last slide. How do you get into RCM? Relatively easy. There are 3 possibilities. You already have kernel code execution due to some other hack, and you can just set this PMC scratch register and reboot, and then the ROM sees this and just goes into the RCM path. You rip off the eMMC board, then it can't boot. It has no other chance than to go into RCM so that we can exploit it. Or you press a magic button combination while turning on the device. The magic button combination is configurable. Either it's volume up or volume up and the home button while turning the thing on. The switch is configured for the latter, so the home button doesn't exist. But Failoverflow found out that here on the side, on the right Joy-Con, where this Joy-Con actually connects down here to some pins, there is this pin for the home button. So they 3D printed this thing on the right that fits exactly into this slot where we just have this bridge. So you put this thing in, you press the home button, you hold plus, turn it on, and you're in RCM, and you can launch the exploit. I don't know if you can already buy these in China somewhere. You can just print it. I printed one of these and hacked the thing that they glued into there is part of a USB connector. So you can just cut this up, solder the 2 pins together. This is the first and the 4th pin, I think, of a micro USB connector. So you just sacrifice a cable and curse a lot because it's just fiddly. And then you have your own of these jigs. That's it. If you want to know more about this, there are more resources. I linked this on the slides here. The first one is the Fusée launcher. That's one of the exploits that got published shortly after the bug was public. It also has a nice write-up if that code thing that I explained to you was too fast for you or too convoluted. You can read up the write-up there by Kate Temkin. It's actually a pretty good write-up. The second one is Chauvel 2. That's the same bug, but a different exploit from fail overflow. They released it shortly after, and they also ported Linux, so you can look at their repositories, you can run Linux on a switch. So yeah. Questions?
How do you know which buffer has been used? Or do you just like extend the jump slide that thing to also cover the same?
Yeah, so the question is, how do we know which buffer of these two is being used? You can just count how many USB transfers you do. So the question is, which of these two buffers are used? Because in my mem copy here, I always assumed that the second buffer is being used, and I copy that over here. You could also do this with the first buffer, but then, I mean, the space here is big enough. It covers all of these three buffers. So you could, for example, just copy this here over to here and overwrite the first buffer, the second buffer, and then the stack. But it is not necessary. You can do both, but what you do is, because these things are used in sequence, so the on the first transfer, this buffer is used. On the second USB transfer, this buffer is used. On the third transfer, this is used again. You can just count how many USB packets you send, and then you know when you used buffer 2 or buffer 1. If you are currently in buffer 1 and you want to want to switch to buffer 2, you can just send another byte over the bulk endpoint, for example, and then this buffer is being used, and then it switches over to the second buffer. And that's actually exactly what that Fusée exploit code does. The code, if you want to try to understand the exploit, definitely look at the Fusée launcher exploit, not at the Chauvel 2, because this code quality is pretty good. It's written in Python, and it's a breeze to read. This Chauvel 2, while being a cool exploit, because it launches core boot and everything to prepare everything for running Linux, it's also exploit quality code. If you read that, it looks like an actual exploit, which is a bit convoluted usually, because you write that exploit and you don't care how it looks like after it works. Yeah, thank you.